Hello guys, I'm Said Malaki, and in this video I'm going to show you how to compute hoop force in axisymmetric analysis through Python scripting. So let me show you what's the problem. Here we have a closure that is used to end an oil pipeline. This is a 48-inch closure that consists of a clamp, a hop, and a door. These three parts constitutes this closure, and we have and at this region it is connected by weldment to the pipeline, and the pressure is applied at this surface, and this surface. Since the problem is axisymmetric, both from the view both from loading conditions and the geometry and the boundary conditions, we can simulate this problem by axisymmetric analysis. However, an important result that should be obtained from the axisymmetric analysis is the hoop force inside the clamp part. This hoop force tries to tear apart the clamp section, and it is needed for further calculation of the clamping force for the clamp part. So let's jump into the problem. This is the Abaqus model. We have three parts: clamp, door, and hop. This is our assembly. We have an axisymmetric analysis. A pressure is applied to inner surfaces of the closure, and the end of hop is constrained in radial and axial directions as the weldment to the pipeline. Okay, we have used quadratic axisymmetric elements. For example, here we have the part clamp. We have used CAX8 elements, which are 8-node by quadratic axisymmetric quadrilateral, and full integration, since we unchecked the reduced integration checkbox. Okay. After the analysis, we have the results here. And this is the results. This is the results. This is 1 Mises stress contours on door, hub, and clamp. And we are interested in the hoop force, which tries to tear apart the clamp, which corresponds to hoop stress. In axisymmetric analysis, hoop stress can be obtained by putting our variable on S33. S33 shows us the variation of the hoop stress on different parts. What we are trying to do is to multiply the value of the hoop stress by the area of the element, area n, and sum it with this value for the next element, and do this loop until we compute all these multiplications for all the elements for the clamp. After performing these multiplications and summing up all these multiplications together, we have the hoop force for the clamp. Okay, and it's not something that we can obtain it, I mean the hoop force, through default output of Abaqus Visualization. We should do it by Python scripting, and this is the actual topic of this video. So let's jump into the Python scripting. I assume that you have some basic knowledge of the Python scripting in Abaqus. So and try to teach you in a fast way. So these are the module that we import in our Python scripting: part module, material module. Maybe we do not need all of them in a Python scripting, but it's better to import most of the Abaqus modules in the beginning of our Python script. But the module that we need for sure in this problem is this module, mesh visualization. We need it. ODB access to access the ODB file. Again, we have this is redundant. I can delete this part because since I imported it earlier on this line. And region toolset, I think I didn't use it, but it's better to have it. Okay. So what we are trying to do is first to open the ODB file, which is this file, by ODB, open ODB method, which is inside the ODB access module. It at least needs one argument, which is path, and this is the name and extension of our ODB, which is in our working directory. Okay, let me bring my working directory here. Okay, this is my working directory, and this is my ODB file. Okay, the next parameter is a string which specifies model name here in our Abaqus model. This is my model name. The next one is the element set, L set name, which is the name of our specific element set. Here in the assembly, I created a set on the clamp element set. So I have very direct access because I want to do my computation on the elements of the clamp. So I created a set on the clamp. Okay, and that is the name of that set. Instance name clamp 1. Here we have it. And part name clamp. Okay. Maybe you should ask why I capitalize all the letters of instance name while it is not capitalized in our model. And the reason is that since I go to ODB object model to extract information, when I use this parameter in the ODB, the name of the instance in the model is capitalized. Let me show you. I go to visualization, and I go here. I'm going to instances, not here. Instances, you can see that these are, while in the model it is not capitalized all the letters, just the first one is capitalized. In the ODB in the ODB, it is all letters are capitalized. You can try it. You can try this one and see what will happen. But I try to be as accurate as the ODB file. And I don't know why Abaqus does that. Okay. So let's go to some theories. And while it is not very complex, I want to, as I said earlier, I want to multiply the hoop stress in each element by its area and do these computation for all the element and sum all the multiplications together to reach the hoop force. But I can directly access to the area of axisymmetric element. What Abaqus gives me in the output is the volume of the elements, which I requested in my model, in step module, in fill output, and in this section. I requested evol, which is element volume, to be written down in my ODB file. Okay. So I do not have access to the area of axisymmetric element directly. I have access to its volume. So, as the definition of the axisymmetric element says, if I have the volume, I can reach to the area of the element by dividing the volume by, I can reach the area by dividing the volume by 2πr. And r is the distance from the axis of the element to the area center of the element. Okay. So first of all, I should compute this, and I have also volume from evol fill output, and then when I compute the distance from the axis, I can reach to area and then do my rest of computations. Okay, so I requested evol. In this line, I extract the evol element volume fill output. It is in the last step, last frame, and this identifies that I'm looking for evol fill output, and put this fill output in an object, in an fill output object by the name evol underline field. I also extract the stress fill outputs and put it in stress field, this line. In the ODB steps, in the last steps, in the last frame, fill output stress. This is its identifier. But I'm not going to use all the stresses. I'm just looking for hoop stress component, which I can reach to it by a stress field get and use the method get a scalar field. It is a method of fill output object in Abaqus model object. From the stress field, I can extract the hoop stress component. This method have some argument which is named component label, and I can put the S33 identifier as the input to this argument. and I can reach to Hooper stress field. In this line, I compute the number of elements on the clamp, length. It is a method ODB root assembly instances, which instance name here, clamp 1, and the elements. This part specify all the elements on the instance clamp 1, and by using this method I can compute the total number of the elements on the clamp. I have the variable here, which is my total hoop force, which is 0 at the beginning of my iteration loop. So for all elements on the clamp, I have a for loop. In the first line, I print my iteration counter. In the second line, I'm going to extract the Hooper stress for element I. I'm doing the computation for the ith element, so I'm extracting in this line the Hooper stress for the ith element. From the Hooper stress field, I use the get subset method of the Hooper stress field, and for the region argument, I specify which element I'm going to extract its Hooper stress, which is this element. ODB root assembly instances, which instance clamp 1, which element ith. And for the stress, we can have the stress for different position in an element. We can have the stress for on the integration points, we have stress on the nodes, or we can stress on one singular position, which is the centroid of the element. Here, I'm interested in one value of Hooper stress for each element, so I pick the Hooper stress at the centroid of the element. So in another argument, as an input to position argument of the get subset method, I specify centroid of the element. And we have here values. Since I have if I specify integration point, since for this element I have 9 integration points, so values, I have 9 values for the Hooper stress for ith element. But since I picked the centroid, I have just one value, and the index of this value is 0. Since Python is 0th index programming language, I should specify the index of my just only one value, which is 0, and I extract the data and put it in the Hooper stress name, which I chose as ELS33STR. I do the same for the volume of the ith element. Eval field gets subset method. In the region, I specify the ith element, and for volume, I have no option as centroid or integration points. The volume of the element is a singular value and have just one element, one value. I specify the 0 as values, and I extract the data and put it in eval variable. In the next line, I compute the number of nodes for each element. In my model, I know the number of nodes for all of the elements on the clamp is 8, but I put this line. It maybe have some teaching purpose. In the case that elements are different and the number of nodes for some of elements may differ from the number of nodes for other elements. This is a general tool, but in this problem I know that that all elements on clamp have 8 nodes. I mean that this line results that the number 8 is put in NMEL nodes, i.e. the number of nodes for element. I can compute the number of nodes for the element from ODB root assembly instances, which is clamp 1, elements I, and the connectivity. You can try, let me tell you something, you can try all of these lines by writing them in the command line interface of the Abaqus and try what will happen. Let me show you that this line results in the number 8. I can copy. Okay, then for this the line I write it here, but I should specify I. For example, I try for example 45. It doesn't matter. I mean the 45th element of the clamp 1 instance, and the number of nodes for this element is 8, as I knew it earlier. But you can the purpose of this was to show you can try all of the lines of your script by writing them and copying them in the CLI and try it one by one to see what each line does. Okay, so in this for loop I'm going to record, or I'm going to retrieve the value of the radial position of the center of the element. Since I have access to the radial position of the coordinates, radial position of the nodes of the element, I should sum all the radial position for all the nodes of the element and divided them by the number of nodes of the element. So for the element I construct a for loop, and for j iterating from 0 to number of L nodes -1, in the first line I compute the node label. I can reach the node label, actual node label from here, ODB root assembly instances, clamp 1, elements I, connectivity j, which is I'm iterating on j. In this line, for example, assume that j is 1. It means that I'm extracting the node label for the first node of the element I, and so on. For j that is 2, I'm computing the node label for the second node of the element I. And what I'm going to do on the next line is to sum the radial position of the jth node of the element I with the previous one. with j minus 1 node of the element I through this line. But here I'm resorting to the model. In the previous line, I'm working on ODB, as you can see here, but in this very specific line, I'm resorting to MDB. Since I can get because I want to use this function, get from label, and get from label just work for the MDB, not ODB. So MDB model name, which I provided earlier here. This is my model name. In my models, I have just one model in my Abaqus. Part name, which is this one, clamp. Here, it is not capitalized. In my model, it is not capitalized. I'm going to, I know the node label. I know the node label of the my specific node, and I want to compute its first coordinate, which in axisymmetric analysis is the radial coordinate. So in my model, in my MBD, in the model, I look for my specific model, the specific part, its nodes, and by the get from label method, which is the specific method of nodes array object, I can, when by specifying the label argument as the node label, I know the node label, I reach to my specific node, and I use one, and I want its coordinates attributes, and I want its 0 coordinate, which is the radial position or the first coordinate. For example, in the two-dimensional analysis, the first coordinate is the x coordinate, second is y, and third is z coordinate. But in axisymmetric analysis, the first coordinate, which is specified by 0 index, is the radial position which I'm looking for. So in this part, I compute the radial position of my specific node and sum it with previous value. At the end of this loop, I sum up all the radial coordinate of my ith element by looping over its nodes. The only thing that remains to do is to divide this summation by the number of the nodes of the element, which is carried out in this line. Okay, and I put it in ELR coordinate. Now from this line on, this variable specifies the radial position of the center of the element. And as I showed you earlier, if I have this value, I can compute the area by dividing the volume by 2PR. And this is done on this line. On this line, I compute the area of the element. And on the last line of my for loop, I multiply the area of the element by the value of its hoop stress and I sum with the previous values. And when I compute all the multiplications and sum the multiplications together, I come out of the for loop and I print the hoop force in my clamp. So let's go and try this Python script on my ODB in visualization. Let's do it from the beginning. Let's close the Abaqus. Go here, copy my working directory. I should open my CAE file. I should have my model open in my CAE, in my Abaqus CAE, since in this line I'm working on the models. Okay, then I will go into visualization, and by the knowledge of that I have my ODB in my working directory, which is this, I can run, and also my model is open, i.e. this. I can go to visualization, file, run a script, and my script, and hit on OK. You can see that I'm iterated on the elements of the clamp, and finally the value of the hoop stress is printed. You can also comment out this line. It's not very traditional to show the iteration counter in this way, and the code then works better. Again, run a script. This time the iteration counter didn't show, and just the value of the hoop for stress is printed. Thank you for watching this video, and I hope that you can find it useful. If you have any question, I would be very thankful if you email me or comment on the below video, on this video.